fingers crossed, I hope this works. This is an interactive black hole flight simulator which is being run by my laptop at the back here, and we're connected wirelessly. So please fasten your seatbelts, because I don't know if this is going to work. You may need it. I was asked to talk about BKL collapse in this talk here. This is a little video here of a visualization of falling into a black hole. I'll talk about that later. But before I do, I wanted to take an excursion into the simpler black hole here, a Schwarzschild black hole. And this is what we have here. It's not very dark. It would help if it were darker here. But, okay, so this is a Schwarzschild black hole. I'm going to put on a little clock here on the right. Again, you can't see this very well. Is it possible to darken the shades a little bit here? Is it possible to take down the shades a little bit here? Yeah.
Maybe that will work. Okay.
Yes. So this is a Schwarzschild black hole, and we're about 20 Schwarzschild radii from the center of the black hole, and we're in orbit around this. And just to make life simple, I've given this black hole the mass of the black hole at the center of our galaxy, 4 million times the mass of the sun. And the reason I've done that is that you can fall through the horizon of such a black hole and not be tidally torn apart, which is very nice for us. Right now, time is going by at 1 second per second, which is the way that it usually does. I'm not sure exactly why time goes by at 1 second per second, but nature seems to prescribe that. I can go forward 1 meter and I can go backwards 1 meter, but I don't have that freedom in time. However, with a black hole flight simulator, one can go faster and faster. So I'm going to speed up time here, and you can see that we're actually in orbit around this black hole. It's still not very black here, is it? Is there anything that goes on here?
We'll ask somebody.
Okay. Okay. It's visible. Good. So one of the things about orbits around black holes, at least if you're far enough away from the black hole, they are stable. So that means if I press on make a little fire on my thrusters, I will go into a stable circular orbit. It's an elliptical orbit, or at least it would be an elliptical orbit if this were Newtonian gravity, but it isn't. So the orbit doesn't. It goes a little bit more than 360 degrees. I can speed this up here so that you can see we're in fact in a quasi-elliptical orbit. So let's slow this down again. I'm now going to do something which is I'm going to throw, I hope. Okay.
Maybe you will start from the beginning.
No, I'm good. I was just wondering, okay, so my mouse, which is working by, maybe you could get out of the way of the laptop there so that I can get a clear view of, it's a little bit, there we go. Thank you very much. So let's fire some objects in here. Gosh, and now I can't see my keyboard. And it's not a lighted keyboard either. So I've been given a keyboard which I'm not familiar with. Let's just try this and let's throw some objects in, and let me see if I can slow this down a little bit. This is going to be absolutely chaotic because I can't see anything here. Let's throw some things. Let's slow this down a bit. This is a cube, by the way. The reason it's flexing, everybody here knows all about relativity. The reason it's flexing, it's not because of the tidal forces. It's because the time travel, the light time travel from the back of the cube is a little bit longer than the light travel time from the front of the cube to us. And so we see the far side of the cube as it used to be relative to the near side of the cube. I wonder if I've managed to get anything into the black hole at this point. Let's just fire a few more just to make sure that we've got some successes here. Success means, and I'm going to speed this up now. Whoops. Success means to fall into the black hole, and you can wonder whether why is it so difficult to fire things into a black hole. Let's see what happens here. Gosh, have we got any successes? I think if you look there on the bottom left, we may have a few successes here. Now, one of the things you notice is that it fell into the black hole and it redshifts and dims. Now, this is something that you can't do in reality. In reality, it keeps dimming and redshifting and you lose it as here. But in a black hole flight simulator, I can kind of, let's get rid of that. I can brighten this up a little bit so that you can see. Can you see this? Can you see any red objects back there? Maybe, maybe not. Some of you can. Let's go into another kind of orbit here. In general relativity, there are also not only stable circular orbits away from the black hole, but there are unstable circular orbits. So let's go into one of those right now. A little fire on our thrusters is all it takes to be able to do that. And let's speed it up a little bit. There we go. Wonderful. There you go. Now we can see these things that are frozen on the horizon. Again, in reality, we would not see these things being red. They would be redshifted into oblivion, but I've brightened them up here so that you can see that they're frozen on the horizon. Yes, we are doing full screen general relativistic ray tracing of everything here in real time. There they are, frozen on the horizon. So why are they frozen on the horizon? We've understood this for a long time. Gosh, this is the inflationary instability, but we'll get back to that in a little while. Come on. The reason things get stuck on the horizon is just an optical illusion. This is a version of the Schwarzschild metric that you undoubtedly this crowd is very familiar with, the Gullstrand-Painlevé metric discovered by Alvar Gullstrand and Paul Painlevé independently in 1921. Alvar Gullstrand did it first, and it looks like that metric up above. It looks like space. It encodes not only a metric, but a tetrad, and that tetrad is falling into the black hole at the Newtonian escape velocity, that v equals minus the square root of 2gm over r. And I've indicated by this arrows out here. So the physical picture that emerges here, the conceptual picture, is that space is falling into the black hole at less than the speed of light outside the horizon, hits the speed of light at the horizon, and then is falling faster than the speed of light inside the horizon. Light, of course, can move through space only at the speed of light, but space itself can kind of do whatever it likes in black holes and cosmology. And it hits in full velocity at the central singularity. So the reason things appear to freeze at the horizon is because light emitted at the horizon pointing outwards goes outwards at the speed of light through space that is effectively falling at the speed of light, and it takes an infinite time to lift off the horizon and make its way to the outside world. An emitter that falls through the horizon really has fallen through the horizon. It just has the impression of getting stuck at the horizon. Okay, so let me do something that, ouch, that hurts a little bit. Real black holes don't come equipped with red grids. You can see that this red grid is a set of lines of latitude and longitude. I can kind of make it a little bit, whoops. Come on, come back. Oh, well, apparently I can't manipulate it very, very easily. Let me get rid of the things. I want to fall into the black hole and see what happens when we fall into the black hole. Excuse me. Sorry, I'm having difficulty because my remote mouse is not quite what... Come on. All I have to do is a fire on my retro thruster, and I hope that'll do. There we go. And that should allow us to fall into the black hole. You can see that we're approaching the horizon. I'm going to slow this down a bit as we fall through the horizon. And here we fall through the horizon. Okay, so this is, if you haven't seen this before, this is quite unexpected. If you've seen it before, you've gotten used to it by now. inside the horizon, I'll stop it right there. Inside the horizon, now the horizon that we've fallen through is this blue-white grid above us, okay? That's the event horizon above us. That's the surface of no return. It looked from outside as though one ought to fall through this red-shifting surface below us, but we don't. We fall through the event horizon, and the horizon gives the appearance classically of splitting into two. You might ask, what is this red grid right here? Well, this red grid isn't the event horizon at all. From the outside, it appeared to be event horizon, but it isn't. It's actually the red-shifting surface of the star that collapsed long ago. Let me show you how this works. This is, again, an accurate visualization of the collapse of a pressureless uniform star to a black hole, first calculated by Robert Oppenheimer and his student Snyder in 1939. And they noticed, I've made it transparent, not because real stars are transparent, nor are they pressureless, and nor are they uniform density, but this is the simplifying assumptions. I've got an outer layer, an intermediate layer, and then a center there. And this is what it looks like from the outside. An outsider does not see the star collapse all the way to a singularity. Rather, it sees the star seem to freeze at the horizon, or what appears to be a horizon. And notice the way the two layers here, the outer layer and the one halfway through, they merge to the same set of grid points. That red-shifting surface is nothing more or less than this thing right here. That is the red-shifting dimming surface of the star that collapsed long ago. An outside observer never sees the star collapse through its horizon. It appears to remain ahead of you. Okay, so there is a misconception, and forgive me if I'm maligning you here, but there does seem to be a misconception in the literature that when you fall down to the horizon of a black hole, somehow you catch up with stuff that's going on at the horizon. For example, Ted Jacobs says this quite explicitly. You go down to the horizon, apparently quantum mechanics is happening at the horizon. There's Hawking radiation at the horizon carries the states of the black hole, and you go down there, surely something strange happens at the horizon. And I think part of the issue is the idea that here's the horizon, and here's light that's emitted at the horizon, that's going up at the speed of light through space. It's falling and it's just sitting there forever. And so that when you fall through the horizon, the event horizon of a black hole, you somehow catch up with that radiation. Either classically or in the quantum case, you catch up with a Hawking radiation that's been sitting there at the horizon, just whizzing away. In the firewall paradox, for example, they talk about Hawking radiation operating semi-classically near the horizon. No, it doesn't. No, it doesn't. There's a very simple, classical counterexample. Imagine you fall through the horizon of a black hole, and you fall through feet first, and there's a point where your feet hit the horizon, go through the outer horizon, and then light emitted by your feet comes up to hit your eyes, and you're falling through the horizon too, and so you catch up with the light from your feet at the horizon. Does that mean you catch up with your feet? No, it doesn't. You don't catch up with your feet. You're in a locally inertial frame. You look down, your feet are still below you. When you fall through the horizon of a black hole, you don't catch up with anything classically. You don't catch up with the red-shifting surface of the star that collapsed long ago, and you certainly don't catch up with anything quantum mechanically either. Why on earth would you? Let's go close to the singularity for a moment, and I'll get back to quantum physics in just a second here. But let's continue this exercise here, and let's have a look at what it looks like near the singularity of the Schwarzschild black hole. I'm going to slow this down because it all happens in kind of a rush. You can see from the clock on the right-hand side that's in seconds, and so I'm slowing this down tremendously. As you approach the singularity, you don't have the impression of reaching a point. You have the impression that this thing is it's a surface. Let's just fall to the singularity be done with it. There we go. We're at the singularity. You don't have a back button, unfortunately, in real life. But in the black hole Fleiss-Diameter, we have a back button, and so we can go back out of the singularity. And I apologize, this is kind of, yeah. It gets tough to do ray tracing near a singularity. You should be impressed by the fact that it doesn't crash here. But it does get tough. The tidal forces are becoming infinite. Okay, so that you appear to be landing on a plane. But right now we have some angular momentum, so let me remove that. Let me pretend we're falling in directly. Here we go. This is now if we were falling in vertically, and we can look around, and the thing looks like a flat plane. And two things I want to bring your attention to. Well, several things. One, there's a flat plane here. One is, here's the event horizon above us, and here is this redshifting dimming surface of the star that collapsed long ago. We started calling this the illusory horizon back in 2010, partly because Don Marolf was claiming that we didn't understand what we were talking about. No, Don, I think you don't understand what you're talking about. Sorry about that. You said it first, that we don't understand. This is the redshifting dimming surface of the star that collapsed long ago. I emphasized the fact that when you fall through the event horizon, you don't catch up with this dimming redshifting surface. But interestingly enough, as you approach the singularity, you have the impression that you catch up with this illusory horizon, the redshifting dimming surface of the star that collapsed long ago. Okay. So let me make a few other points here. This is a conference, and one of the things that one does at conferences is one makes outrageous statements. When I do this in published papers, or at least in papers that, you know, you've seen this before. You get a referee, or you get two referees, and one referee says, this is wrong, and the other referee says, this is well known. Right? Okay, so this is one of those things that is both wrong and well known, and we can debate this. I would claim that the singularity of a Schwarzschild black hole is a surface and not a point. Now, it looks like a point because there's a singularity right here. But let's do a thought experiment. Here's two people, a blue person who falls in radially. They're just going with the flow. They're not accelerating or anything. They hit infinite velocity at the singularity. Here's another purple person doing the same thing. And one can ask, is the blue person in causal contact with the purple person? Well, this gray boundary right here is the boundary of the pass light cone of the blue person. The gray region is defined by photons which have the maximum angular transverse motion compared to their radial motion. Again, inside the horizon of a black hole, space is effectively falling faster than the speed of light, and photons, whichever direction they're trying to go, outwards, inwards, sideways, wherever, they always must progress inwards to smaller radius as time goes by. And the boundary here of this gray thing delineates precisely those photons that have the maximum angular momentum. Technically, angular momentum per unit energy of going to infinity here. So the last that the blue person sees of the purple person is right here. Likewise, the last the purple person sees of the blue person is symmetrically right here. So they lose causal contact with each other already well away from the singularity. And the fact that it appears that the blue person and the purple person meet at the singularity isn't true. They have already lost causal contact with each other, right? To encounter each other at the singularity, it would be like I have to fist bump you, and I would have to fist bump you at faster than the speed of light to meet at the singularity. Now, I want to make a little cautionary here. What I'm talking about here is asymptotically close to the singularity, but not at the singularity. I'm not talking about quantum gravity here. I'm just saying, take the limit as you go towards the singularity. You are out of causal contact.
Singularity is very special. What would happen if you have a curved singularity?
Wait! It's exactly the same thing. It's exactly the same thing. The surface, the singularity of a Kerr black hole is likewise a surface that happens at the inner horizon.
It's a ring.
It's a ring? No, it's not. Not if we're going to talk about that. Okay, you just
this movie Interstellar. Do you remember this movie?
Yes, the gentle singularity. Yes, I talked to Kip Thorne about this, and I told him, no, Kip, you're wrong. Again, his source was Don Maroff, and Don Maroff is not a reliable source. Okay. I will tell you what the truth of this matter is, and we can debate about this, but this is a conference, so we can have lively things. Okay, just to make the point that the singularity is a surface and not a point, that is to say, two people who fall along two different angular directions hit a different point on the singularity, at least in the limit, okay? So this little thing here is the shortest causal path between the blue person and the red person. You can see this part of that causal path is the boundary of the light cone of the blue person, and this is likewise the boundary of the light cone of the purple person. This thing here, by the way, yes, it is a cardioid here. So usually, when I go close to you, right, we are getting closer causal contact, and I get louder and stuff like that. But near the singularity of a black hole, that doesn't happen. Even though our spatial distance, as measured by the angular distance between these 2 points, is going to 0, at the singularity of the Schwarzschild black hole, the shortest causal path, that of null rays, which I've drawn here, is finite. So I think one has to draw the conclusion that the singularity, okay, that the singularity is a surface, yes.
What you're describing is asymptotic silence. Each one will only see.
Yes. Thank you very much.
And we have proved this for many models since 2003.
Thank you, sir. Right. So you've said exactly right. So you're the referee who says this is well known.
No, I don't.
And there are others who will say that it's wrong.
What I'm saying is that what we have described as asymptotic silence.
Thank you. Okay. So curiously enough, it's not silent. At least it's not silent when you introduce Hawking radiation here. Calculating the Hawking radiation inside a black hole is not a trivial thing. This was attempted after Hawking 1974 and during the early 80s, and basically there was a failed attempt to discover what the Hawking radiation inside a black hole is, at least from a rigorous mathematical level. Now, as an undergraduate, I studied pure mathematics, but then I saw the light and I converted to botany. I'm sorry, we call it astronomy and astrophysics. And in astronomy and astrophysics, we're quite happy to wave our hands a little bit in order to get the right answer. So Istvan, wherever you are, sorry to insult you. There you go. This is not a rigorous calculation, but a calculation that one can do to estimate the Hawking radiation here near the singularity is to calculate the acceleration on the, again, the redshifting dimming surface, which we're calling the illusory horizon, that right here. And that acceleration, which one can calculate in the classical geometric optics limit, goes to infinity. Let me show you that right here. So one can calculate, this is the acceleration seen on the illusory horizon below. It goes over to the classical value of 1/4, far from the black hole. And as you fall through the horizon here, the event horizon, it remains finite, but then it diverges as you approach the singularity. The idea that Hawking radiation diverges near the singularity shouldn't surprise you at all. At the singularity, the curvature is becoming infinite. That means the tidal force is becoming infinite. How can you possibly imagine that an infinite tidal force would not tear apart pairs of quantum mechanical pairs, and you would get rampant Hawking radiation resulting from that? What makes it rather interesting here is when you do the actual calculation, you also find that there's Hawking radiation from the sky above. Example, if I look up at the sky above, I see that the sky above is also redshifted. The reason it's redshifted is I'm falling into the black hole, so I'm accelerating away from the sky above. So instead of at the illusory horizon where stuff is kind of accelerating away from it, we're accelerating away from the sky above, and there's Hawking radiation associated with that. If you like, you can call it Unruh radiation. It's all the same thing. And as you approach the singularity, those two become the same. And more generally, this is looking directly up and directly down. This is looking at various viewing angles, and it looks like the the radiation is becoming isotropic as you approach the singularity. And one can calculate the amount of energy density, and it diverges near the singularity. So I'll just make a few musings on the Schwarzschild singularity. Again, this is not quantum gravity. This is just taking classical general relativity plus quantum field theory and curved space-time and asking what happens near the singularity. Classically, the Schwarzschild singularity is a three-dimensional spatial boundary of four-dimensional space-time. That is to say, when you hit the singularity classically, it's the time dimension that comes to an end. I think Jose would agree with that. But quantum mechanically, if unitarity holds, then the singularity is a two-dimensional spatial surface, as Belinskii and Hawking showed us. The entropy is equal to a quarter of the area of the horizon. And that third spatial dimension must become an emergent time dimension. I have no idea what that means. That's why I've called it musing. But it must be if you require that unitarity holds. This is closely related with the information paradox. I would like to know if there are any string theorists around here, because I'm not a string theorist, but it looks to me, it sniffs to me like the singular surface is a two-brane. But I might be wrong about that. And just for fun, I'm going to turn on some Hawking radiation here. There we go. Just before this conference, I made a cheesy little diagram here of this actually has, I've blue shifted these and made them. There's some mathematics that goes in here, but it's kind of cheesy, okay? That's my best. Let's sort of, let me go away from the black hole. It gets, if we go away from the black hole, it gets cooler. And as you approach the singularity, it gets hotter. It's difficult to see. These are black body colors. Boom, there it is. My best guess. Okay, so let me go on to what I'm supposed to be talking about, which is a Kerr black hole. This is the again, this is properly drawn here. This is the Kerr geometry. And as you said, it has a ring singularity here. Because of the centrifugal force, it bulges out into these beautiful ellipses. These are confocal ellipses. There's an outer horizon, and there's an inner horizon, and there's a ring singularity at the common focus of those two ellipses. Actually, they're spheroids of rotation, the rotation axis being around here. And as you're probably aware, there's all kinds of crazy stuff, like if you go through the r equals 0 ellipsoidal coordinate into r negative, which corresponds to the antiverse, and there's a place that I call the sissy tube. They should have a name for this. It's where you go, if you go retrograde fast enough, as Brandon Carter showed us in 1967 in his PhD thesis, you can go back into your past and you can shoot yourself and violate causality, closed time-like term. I'd call it sissy tube because it needs a name, for goodness sakes, and it's a tube that's adjacent to the singularity. And it's after Sisyphus, who kept climbing up the mountain and had to repeat what he was saying over and over and over again, and had to repeat what he was saying over and over again, and had to repeat what... Luckily, we're not in a sissy tube here. However, okay, so let me explain a little bit about what's going on, and then I'll show you with a black hole flight simulator one. Here's space falling in, hits the speed of light at the outer horizon, goes faster than the speed of light inside the outer horizon, and then because of the centrifugal force, it slows back down to the speed of light, which divides the inner horizon. The inner horizon is the gateway to all kinds of crazy stuff. So let me go back to here. Let me back up. I'm going to turn off the Hawking radiation. We're going to turn back on the horizon, get out of this black hole. We're going in time reverse, which we're not allowed to do. And the reason I'm going to do this, I'm going to turn this into let's give it a slightly different orientation. I'm going to turn this into a Reisner-Nordstrom black hole. This is a Reisner-Nordstrom black hole. Let's just get in there. Okay, I can't do Kerr black holes yet in the black hole flight simulator, but the Reisner-Nordstrom geometry also has an inner horizon. And the phenomenology at the inner horizon of a Reisner-Nordstrom black hole is similar to to a Kerr geometry. One day I do hope to do a rotating black hole, but I haven't been able to do that. Okay, where are we going here? Can we go in? Let's see if I can. Let's see if we can go in here. Excellent. Okay. So we're back in an unstable circular orbit here. Very convenient, by the way. When future civilizations visit supermassive black holes, again, it has to be a supermassive black hole so you don't get tidally torn apart. There's this welcoming mat just around the black hole, which is called unstable circular orbits. All you have to do is fire on your maneuvering thrusters just a little bit and you can get into a stable or unstable circular orbit. And then fire on your maneuvering thrusters and you can escape back out to infinity, which is so cool. Who ordered that? But God has it ready for us if we need it. Of course, you have to be sure not to press the back button. If you do a retro fire instead of a forward fire, you will fall into the black hole. So let's do that. Let's slow this down again, and let's fall in. There we go. And let's see what happens here. Again, this is a Riemann-Nordström black hole. Come on. No. Yes, we went through a wormhole. I want to slow this. There we go. So once again, we fall through the outer horizon. The outer horizon, the event horizon, the true horizon is that blue shifted, white blue shifted things. The coloring here is not exact. These are colored with black body colors. So blue means kind of blue shifted around here. And this thing below us is the illusory horizon, the red shifting dimming surface of the star that collapsed long ago. For a while, it looks very similar to what happens in the Schwarzschild geometry. But as we approach let's speed it up just a little bit. As we approach the inner horizon, as we approach the inner horizon, come on, slow down. It appears as though we're going away from the black hole, but that's just a special relativistic effect. We're actually accelerating towards that thing, and it's being aberrated in the direction that we're moving, and it's becoming more and more blue shifted. You see this brightening thing around here. And as we hit the inner horizon, which is just, there we go. Boom. As we hit the inner horizon, I'm going to remove the grid so that you can see what's going on. You see the outside universe infinitely blue shifted. One of you pointed out, I think it was Ishtvan that pointed out, when you pass through the inner horizon of a black hole, you see future infinity, or at least you see something. This was first pointed out by Roger Penrose. When you fall through the inner horizon of a black hole, you will see the outside universe infinitely blue shifted. And let me explain a little bit about what's going on there. Okay. So crazy stuff happens when you pass through the inner horizon of a black hole. In particular, Roger Penrose first pointed out that a person crossing an inner horizon would see the outside universe infinitely blue shifted. And that remained kind of a conjecture for a while, but Eric Poisson and Werner Israel in 1990 clarified the full nonlinear nature of the instability, which they called mass inflation. Mass inflation is driven by cross-flow between outgoing streams and ingoing streams near the inner horizon. They're actually not in the analytically extended Kerr geometry or Riemann-Nordström geometry. It doesn't matter. There are two inner horizons, an ingoing inner horizon and an outgoing inner horizon. Stuff that starts in the universe here falls through the black hole. If stuff is moving retrograde, it turns around and becomes outgoing. If stuff is moving prograde, it turns to remain ingoing. And as the ingoing and outgoing streams approach the inner horizon, they become infinitely blue shifted relative to each other. One way to understand this is looking at the sign of time, which way time goes. In the universe, time goes in the usual way. In the black hole, time becomes a spatial dimension. But inside the inner horizon, time reverts to its normal behavior, and there's a version of the wormhole here, I call it the wormhole, where time goes forwards, and another where time goes backwards. So outgoing stuff goes into this regime here, where time is going backwards, and ingoing stuff falls through here. And so you can see these two streams, in order to reach these two causally disconnected pieces of space-time, have to exceed the speed of light. Mass inflation, I'll read this, is caused by relativistic counterstreaming between ingoing and outgoing streams near the inner horizon. To drop through the inner horizon, the streams must exceed the speed of light relative to each other, which they cannot do. In other words, this infinitely bright, infinitely blue-shifted thing that Roger Penrose has pointed out, that corresponds to stuff that is moving at the speed of light, streams streaming through each other at the speed of light, which is impossible. The back reaction, in reality, however tiny the streams are, even an infinitesimal stream, their energy density in the proper frame of those counterstreaming things will eventually back react on the geometry and destroy it. So in reality, inflation, Poisson Israel inflation, is driven by accretion. It's it. Freely falling particles with sufficient angular momentum prograde become outgoing at the inner horizon. Essentially, they have extra angular momentum, which is enough to kind of turn them around so that they become outgoing, going against the flow of the inflow of space-time. Whereas particles or fields with sufficient angular momentum retrograde remain ingoing. Of course, everything's ingoing at the outer horizon. But the stuff with extra angular momentum turns around. One of the remarkable things that Poisson Israel first showed, the smaller the accretion rate, the more rapidly inflation exponentiates. That is to say, the scale length is proportional to the accretion rate. And the smaller the scale length, the smaller the exponential scale length, the faster inflation increases. So this is kind of weird. Usually one is used to an instability where the smaller the influence, the smaller the smaller the effect. But here it's kind of different, that the smaller the influence, the smaller the accretion flow is, the more rapidly things grow. So it's a very violent instability. Poisson and Israel, in their original paper, considered that an isolated black hole, in which the ingoing and outgoing accretion flows were driven by gravitational radiation. That certainly happens, but gravitational radiation decreases very rapidly with time. The quadrupole, which is the slowest decaying, the energy density that decreases as t to the minus 12, and higher multipoles decrease even faster than that. So if you just include gravitational wave energy, the curvature diverges, causing the curvature to diverge in such a short time that the space-time remains scarcely distorted. And this is the weak null singularity. Real black holes, on the other hand, accrete. And for any finite accretion rate, inflation is followed by collapse and not by a weak null singularity. Now, one of you asked about the work of de Fermos and Luke. It's a beautiful piece of mathematics, but it considers a black hole which is effectively isolated, and that never ever happens in the real universe. And even if one could consider a black hole that remained isolated forever, so that the only thing that was feeding it is gravitational waves, that ignores the fact that one of the consequences of this a weak null singularity, what is it? The tidal force is becoming infinite, and if the tidal force is becoming infinite, you cannot ignore quantum effects. Hawking radiation, pairs will be torn about by an infinite tidal force. And to neglect quantum effects and to neglect accretion, I would say, it doesn't invalidate de Fermos's and Luke's work, but it means that it is not relevant to reality, and that is a fact. Okay. One of the things that I've been very interested in doing, it's been a policy I've been trying to follow for many years, is rather than try and attack the singularity directly, to do everything that you possibly can, all the calculations that you can do to get up to the singularity. So one of the things that I've been trying to do was calculate what happens as a result of inflation. Again, if you have an accreting black hole, you will get Poisson Israel mass inflation. But what happens after that? Again, if the accretion rate goes to 0, you get a weak null singularity. Fine. But if the accretion rate continues, as in the real case, then one gets a different outcome. And I will show you that it's BKL. But before I do that, I want to put up this complicated graph here and say, as all of you know, most of the work that goes into any calculation is the kind of completely difficult stuff. What I'm about to show you is the results of a numerical calculation, which shows that inflation develops into BKL singularity type behavior. The calculation is a numerical calculation with all 6 degrees of freedom of the gravitational field. And it's a very challenging thing, because during inflation, the energy momentum is diverging, the curvature is diverging, you're approaching a singularity. Everything is getting very difficult. By comparison, I would say gravitational waves, it's easy. So this was my attempt to try and understand this. I used, the practical method that I used was based on the mathematical language of multi-vector valued differential forms. And in those, the system is defined by a 16-component line interval. That E here, this is the 4x4 Vierbein matrix here. This is the 16-component line interval. And then there's a Lorentz connection with a bivector 1 form. The Hilbert-Lagrangian takes this Hamiltonian form, and then Hamilton's equations, 40 of them, comprise evolution equations for the line interval and the momentum conjugate to that. This is that thing here. Again, I don't want to mess with that. This works for electromagnetism, supergravity. Here's the result that I was asked really to talk about, which is the final result of this. You're going to hear more about BKL instabilities later on in this. But basically, the BKL behavior is described by essentially following material. And again, what we've got here is streams that we've got some real energy momentum here, and you can go into the rest frame of the energy momentum, and in the rest frame of the energy momentum you can follow the distortion of the space-time. And as BKL showed, you can think of the space-time, the spatial space-time, as kind of like a football, an ellipsoid with 3 different axes. And in BKL behavior, the behavior of those axes is described by 3 power laws. There's 3 cosmic scale factors, AI I've called them here, and each varies as time as t to the q, wherever I've got that here. And the sum of the q's is 1, the sum of the indices of the square of the indices is also 1, and that is BKL behavior. So I was able to show, as a result of starting with inflationary initial conditions, I was able to follow this. And you can see these are 3 scale factors following the football. This is a rotating black hole, and there's not so there's these 4 power law epochs, first one here, then another one here, each varying as a power law with a mean scale factor. And between the power laws, there's bounces. So there's 1, 2, 3 bounces. And then the thing gives up at this point, numerically gives up, because the energy density is hitting 10 to the 200 or 300 or something like that, which is unfortunate. So I can't follow more than 4 Kasner epochs. But it looks really very much like Kasner epochs. These are power laws. And at each bounce, there's also a slight rotation of that football, which I haven't included. I mean, I have included in the calculation, but I haven't shown it. No, it's not vacuum. This is an accretion flow. I have 2 collisionless streams that are focusing along the ingoing and outgoing null directions. For small accretion rates, in this case, I've got an accretion rate. I've written them down here. There's an outgoing accretion rate of 0.03, ingoing accretion rate of 0.01 in black hole units. Okay, so it's small accretion rates, small enough that you get hyperrelativistic accretion. That is the source of the energy momentum here. I just want to make a comment that there's an inflationary zone which has Kasner exponents which satisfy a BKL thing. So you can think of inflation as being the first BKL epoch. And then there's a regime which I call conformal collapse. Back in 2010, I published a series of papers showing the existence of conformally separable space-times that produced by inflation. They fail at small scales, but it turns out that those conformally separable solutions for accreting black holes correspond to the second BKL epoch. And here, numerically, I find third and fourth epochs. These are the sum of these are the Casimir exponents, which by definition here are sum to 1. And this is the sum of the squares is black. And you can see that, at least during the Casimir epochs, this is about equal to 1. Not equal to 1 at the bounces. And I'm done here. And I will leave you with this 1-minute video, which was done for a NOVA documentary, which shows falling into a Horizon-Nordstrom black hole. This is a general relativistic supercomputer simulation of the accretion flow around a black hole, which is taken into account. You can see a jet coming off. Again, the red shifts and blue shifts, they're not realistic. I've just colored the scene with black body colors appropriate to the red shift and blue shift. At this point, we're about at the horizon at this point, and we're approaching the inner horizon. And the timing is not correct because everything happens in a tremendous rush as you approach the central singularity. But here is the depiction of what it looks like, the best that I can do in Horizon-Nordstrom geometry, of the inflationary instability and the enormously energetic energy momentum that anybody encounters at the inner horizon. That will destroy the inner horizon, and the result is going to be that there is a singular surface at the inner horizon, just like in Schwarzschild. I'm done. Thank you very much.
So, in your BKL, does this mean that the inner horizon becomes a spacelike surface now? Singularity?
Yes, again, I don't get to the singularity. With the BKL, I kind of run numerically. It looks like it's going to hit a singularity. I don't know if there's going to be more than 3 bounces. Maybe there is. It looks more like a Bianchi type 7 with a non-zero K model than a Bianchi 9. I don't know if that's significant or anything. But yes, general relativistically, it looks like what you're going to end up with is a space-like surface at the inner horizon, which is a singular surface. But in carrying out this calculation, I made some approximations, which are roughly equivalent to the assumption that the BKL assumption of homogeneity. I didn't assume vanishing angular gradients, but I took the angular gradients to be those of Kerr. Part of the problem is that as you get closer and closer to the, quote, singularity, the causal size of the causal patch that you're covering gets smaller and smaller and smaller. So to do a complete calculation, you would have to include an exponentially growing number of causal patches. So that is something that will have to be done in future work. I'm probably not going to do it because it's just too challenging. It's already too challenging to do this numerical work. Yes.
I would like to comment because there was this issue about the causal nature of the singularity, and also the famous result, how these things matching to each other. First of all, the result of the famous was an exact analytic investigation of a near Horizon-Nordstrom space-time, and the singularity he ended up was a null singularity, and what he showed using energy estimate methods was to prove that there is a continuous, a possibility of to extend the metric in a continuous way. Now go back to the result which I was talking about, or are talking about. If you don't have C or local Lifshitz extension, then you can be sure that there will be a tidal force flowing up as you approach the horizon. The techniques which were used by Duff-Fermis were energy estimates, and those are about some sort of norms of certain functions developing, coupled to each other, and how these depend on time. When I attended a talk by him, I asked him whether he could calculate the tidal force tensor components of the curvature tensor. Of course not, because the techniques applied by that investigations are completely different from the you know, arguments or quantities used in this extension stuff or in this BKL type investigation. So
can I comment on that?
Yeah.
Yes. Again, I don't dispute the validity of de Fermos's theorems given its assumptions. What I'm saying is assumptions are not those that nature provides us with. For example, if a stellar-sized black hole collapses, it takes about 10 to the 4 crossing times, or about 1 second or a couple of seconds before the energy in the gravitational radiation falls below that of the cosmic microwave background. So accretion from the cosmic microwave background, which is absolutely there, guaranteed to be there, will be more important than what de Fermos is including. And again, even if you didn't have that, the diverging tidal force means that you cannot ignore pairs, Hawking pairs, being tidally torn out of the vacuum. So it's a nice exercise in mathematics, but I don't think it has any relevance to reality. And I'm sorry to be quite so insistent on that. I have referenced de Fermos's papers for many years now, and he has not given me the courtesy of referencing me once. So if he did that, I would love to have a conversation with him instead of just throwing darts at him and it hits the dartboard and never comes back. You're welcome to convey that opinion to him.
But even so, Alice presented his result 2 years ago at the first conference, and I asked him, does this say really anything about the singularity? And you could have a spacelike singularity, you could have a spacelike plus null singularity, you could have a null singularity. It doesn't commit to that, at least not when it's fractured. So even within that mathematical context, he's not really discussing this. And then, of course, if you go outside the context of what he's discussing, anything is possible.
What you're really saying is once you pass the Cauchy horizon, things are unpredictable. So, yes.
So, well, the reason why you see behind type 7 is because you are within an era. So you only have 2 bounces. You have to continue to see that you actually get BKL. Actually, generalities of BKL as we would have on Friday. Because BKL is not a full story about spacelike singularities.